Hi everyone. I welcome you all in the next lecture of ethanol production series. So in previous lecture we have studied about what is engines knocking, and I have discussed all these process of engine knocking at different stages where normal combustion occurs, where pre-ignition occurs, and then what are the consequences of pre-ignition over knocking. And then we have understood the concept regarding octane number for various fuels. And then we have also seen that how we can calculate the octane number using the reference fuels, that is isooctane and n-heptane. We have also seen how many types of octane numbers are there. There were two types of octane number. That was research octane number, RON, and then the motor octane number, that was MON. And then we answered two important questions. The first question was, why does ethanol have such a high octane number? And then why does ethanol have high heat of vaporization? And the answer comes from the chemical structure of ethanol. So the presence of oxygen atom in the ethanol molecule is responsible for making hydrogen bond. And due to the presence of hydrogen bond, you need high amount of heat to vaporize the ethanol molecules compared to the mixture of hydrocarbon, which is called the petrol. And we have seen that ethanol equals of the two times of the order of magnitude of heat of vaporization compared to the petrol. Then we also answer the question like, why does ethanol have high heat of vaporization? And the answer comes from the hydrogen bonding only. So that was very important concept. So in today's lecture, we are going to answer another important question, and this is very important. Like, how does a higher octane number enables more efficient engine? So as we have seen in the previous lecture, that ethanol has a higher octane number, that is from 108 to 109. And if octane number is high, then whether that can enable more efficient engine or not. And in order to answer these things, first let's compare what happens inside a petrol engine and a ethanol engine during the combustion stage. So if we start with both of these both engine cases, in both cases, what happens? The process begins in the same way. So the air and fuel mixture enters in the cylinder, and the piston starts moving, upward. So here you can see this piston will move upward after entering the air and fuel mixture. And then what happens? Due to increase in pressure, I mean, here you will see, if you assume this one is the ideal gas, then if volume is decreasing, then the pressure will increase, and then due to increase in pressure, the temperature will also increase. Now imagine that we want to extract more work from the engine by increasing the compression ratio. So the compression ratio is the final volume divided by initial volume. So our maximum volume divided by minimum volume, right? Already I've discussed this in my previous lecture. But in a petrol engine, what happens? This creates a problem. So if you increase the compression ratio, what happens? Since petrol molecules are, mixture of various hydrocarbons, and as I have told you, the hydrocarbons are connected by weak van der Waals forces of air traction, that is the uh, London and dispersion forces. And we have also seen that the latent heat of evaporation or heat of evaporation was only 340 odd kilojoule per kg. So what happens in petrol, if you increase the compression beyond a certain limit, the molecules will get fragmented and it generates the free radical. And due to the generation of the free radical in petrol engine, what happens? At lower number, the mixture gets compressed, or the compressed mixture may become so hot that ignites on its own before the spark plug fires. So it won't wait for the a spark from the spark plug. And this unwanted auto ignition causes or you can say create a problem, because uh, again, this auto ignition causes engines knocking, and that produces pressure waves that reduces engine's performance and may even damage engine components. So to avoid knocking, what happens? Engineers are forced to design a petrol engine with a relatively lower compression ratio, such as 8 is to 1 or 9 is to 1. So at lower compression ratio, you will see that will produce a lower thermal efficiency. So engine cannot extract the maximum possible work from the fuel. Right. So that's why at a lower octane number, you have seen that this reduces the engine performance. Then coming to the if you changes the engine, like if you use different fuel, like if you changes the petrol to the ethanol, then the initial steps are exactly the same. Again, the air fuel mixture will enter into the cylinder, and then the piston will compress the mixture. However, ethanol has much higher octane number, right? So there is a bandwidth here that you can compress it more. You can go beyond 8 is to 1 ratio to 10 is to 1, 12 is to 1, and you can go for higher compression ratio. So why it is facilitating higher compression ratio? Because ethanol molecules are bonded with the hydrogen bond, and hydrogen bond is a strong bond, right, compared to the weak van der Waals forces of attraction. So it basically it won't get fragmented, like it won't create a free radical like hydrocarbon molecules. So this control the combustion. And like in case of petrol, it was a pre-ignition that was taking place due to the fragmentation of the molecules, and due to the formation of the free radical. But here you won't see any kind of free radical generation, and that's why it avoids the auto ignition, or it will be resistance to the auto ignition. Even when the mixture is compressed to much higher pressure and the temperature, it does not ignite prematurely, and instead it waits until the spark plug produces a spark at the correct moment. And this controlled combustion allow engineers to safely design engine with a higher compression ratio, such as 10 is to 1, 11 is to 1, and even 12 is to 1. So according to the Otto cycle, what happens? Increasing the compression ratio that improves the thermal efficiency. That means you can extract more amount of work from the compression or while compressing the fuels. So therefore, the real advantage of using ethanol as a fuel is not that it contains more energy per liter, but it actually contains less energy than the petrol. But that is a high octane number that enables, higher compression ratio, allowing a properly designed engine to operate more efficient and extract more useful work from the fuels. I hope this is clear to all of you. Now, then coming to the next question, that how does a higher octane number enable more efficient engine? That is the same question, but you can answer this using this mathematics as well. So when we define the engine efficiency, that is 1 minus 1 upon R to the power gamma minus 1, where eta is the thermal efficiency, R is the compression ratio, and the gamma is the specific heat or ratio. That is the ratio of a specific heat. So let's assuming for petrol and ethanol, it is approximately 1.4, and R is the volume, maximum volume divided by minimum volume. What do you mean by maximum volume? That is the cylinder volume when the position is at the bottom dead center. That is called as the BDC. And minimum volume is the cylinder volume when the position at the top dead center. That is called as the TDC. So if you see this plot, you can clearly observe that if we are increasing the compression ratio from 8 to 15, what happens? The thermal efficiency at lower compression ratio, it was increasing more. So you can see it was increasing from 56 to 58, 58 to 60, 60 to 62. One. So here the increase was two of order of the plus 2, something like that. But when it reaches to approximately 11 to 12 compression ratio, the thermal efficiency is not increasing too much, right? So the improvement becomes smaller at the later stage of the compression. So this means increasing the compression ratio always improves engine efficiency, but the gain gradually diminishes at the later stage or at a higher compression ratio. So the challenge is that the conventional petrol starts knocking at a higher compression ratio, but ethanol is having higher octane number 108 to 109 that resists the knocking, and then therefore this allows engine significantly designed for ethanol to operate safely at a higher compression ratio and extracting more useful work from the fuel. So as a conclusion, we can say that a high octane number does not directly, increases engine efficiency. Rather, it allows engineers to design, engine with higher compression ratio, and it is this higher compression ratio that ultimately improves the thermal efficiency. Okay, I hope this is clear to all of you. So in this lecture, we have studied whether higher octane number allows higher thermal efficiency or not. So I'll stop this lecture here only. In the next lecture, we will see the next question, that does every car become more efficient with the E20 fuels? So we'll answer this question. So stay tuned with this lecture series. This is very important to understand for the perspective of as a citizen also, because we should know if we are driving any vehicle, we should know which fuel is, beneficial for our car or our vehicle, and then we should take that fuels also. So I'll stop this lecture here. See you in the next lecture. Thank you.